Chapter 6. The 17th Century. The rapid development of mathematics during the Renaissance was due not only to the practical needs of the commercial classes, but also to the productive use and improvement of machines. Machines were known to the Orient and to classical antiquity. They had inspired the genius of Archimedes. However, the existence of slavery and the absence of economically progressive urban life hindered the use of machines in these older societies. This is indicated by the works of Heron, where machines are described, but only for amusement or deception. In the later Middle Ages, machines were used in small manufacturing, public works, and mining. These enterprises were often undertaken by city merchants or princes seeking quick money, sometimes in opposition to the city guilds. Warfare and navigation also stimulated the perfection of tools and their replacement by machines. A well-established silk industry existed in Lucca and Venice as early as the 14th century, based on division of labor and the use of water power. In the 15th century, mining in Central Europe developed into a capitalistic industry, technically relying on pumps and hoisting machines that allowed deeper excavation. The invention of firearms and printing, the construction of windmills and canals, and the building of ocean-sailing ships required engineering skill and increased technical awareness. The perfection of clocks, useful for astronomy and navigation and often installed in public places, showcased advanced mechanisms to the public. Their regularity and accuracy deeply impressed philosophers. And during the Renaissance and even later, the clock was taken as a model of the universe. This was an important factor in the development of the mechanical conception of the world. Machines led to theoretical mechanics and the scientific study of motion and change in general. Antiquity had already produced texts on statics, and the new study of theoretical mechanics naturally based itself on the statics of classical authors. Books on machines appeared long before the invention of printing. First as empirical descriptions, Kaiser, early 15th century, and later as more theoretical ones, such as Leon Battista Alberti's book on architecture, around 1450, and the writings of Leonardo da Vinci, around 1500. Leonardo's manuscripts contain the beginnings of a definite mechanistic theory of nature. Tartaglia, in his Nuova Scienza, 1537, discussed the construction of clocks and the orbit of projectiles, but had not yet found the parabolic orbit, first discovered by Galileo. The publication of Latin editions of Heron and Archimedes stimulated this kind of research, especially F. Andino's edition of Archimedes, which appeared in 1558 and brought the ancient method of integration within reach of mathematicians. Comandino himself applied these methods to the computation of centers of gravity, 1565. Though with less rigor than his master. This computation of centers of gravity remained a favorite topic among Archimedean scholars, who used their study of statics to gain a working knowledge of the rudiments of what we now recognize as calculus. Outstanding among these students of Archimedes were Simon Stevin, who wrote on centers of gravity and hydraulics, both in 1586, Luca Valerio, who wrote on centers of gravity in 1604, and on the quadrature of the parabola in 1606, and Paul Guldin, in whose Centrobarica, 1641, we find the so-called theorem of Guldin on centroids, already explained by Pappus. Following the early pioneers came the great works of Kepler, Cavalieri, and Torricelli, who evolved methods that eventually led to the invention of calculus. Typical of these authors was their willingness to abandon Archimedean rigor for considerations often based on non-rigorous, sometimes atomic, assumptions, probably without knowing that Archimedes, in his letter to Eratosthenes, had also used such methods for their heuristic value. This was partly due to impatience with scholasticism among some, though not all, of these authors, since several of the pioneers were Catholic priests trained in scholasticism. The main reason was the desire for results, which the Greek method could not provide quickly. The revolution in astronomy, connected with the names of Copernicus, Tycho Brahe, and Kepler, opened new visions of man's place in the universe and man's power to explain astronomical phenomena rationally. The possibility of celestial mechanics to supplement terrestrial mechanics increased the boldness of scientists. In the works of Johann Kepler, The stimulating influence of the new astronomy on problems involving large computations and infinitesimal considerations is particularly evident. Kepler even ventured into volume computation for its own sake. And in his Stereometria Doliorum Vinorum, solid geometry of wine barrels, 1615, evaluated the volumes of solids obtained by rotating segments of conic sections about an axis in their plane. He broke with Archimedean rigor, describing the area of a circle as composed of an infinity of triangles with a common vertex at the center, and a sphere as consisting of an infinity of pointed pyramids. Kepler acknowledged that Archimedes' proofs were absolutely rigorous, perfect in all respects, but left them to those who wished to indulge in exact demonstrations. Each successive author was free to find his own kind of rigor, or lack of rigor, for himself. To Galilei, we owe the new mechanics of freely falling bodies, the beginning of the theory of elasticity, and a spirited defense of the Copernican system. Above all, we owe to Galileo the spirit of modern science based on the harmony of experiment and theory. In the Discorsi, 1638, Galileo was led to the mathematical study of motion and the relationship between distance, velocity, and acceleration. He never gave a systematic explanation of his ideas on calculus, leaving this to his pupils, Torricelli and Cavalieri. Indeed, Galileo's ideas on these mathematical questions were quite original, as appears from his remark that neither is the number of squares less than the totality of all numbers, nor the latter greater than the former. This defense of the actually infinite, given by Salviati in the Discorsi, was consciously directed against the Aristotelian and scholastic position represented by Simplicio. The Discorsi also contain the parabolic orbit of the projectile, with tables for height and range as functions of the angle of elevation and given initial velocity. Salviati also notes that the catenary looks like a parabola, but does not give a precise description of the curve. The time had now arrived for a first systematic exposition of the results reached so far in what we now call calculus. This exposition appeared in the Geometria Indivisibilibus Continuorum, 1635, by Bonaventura Cavalieri Toccia, a professor at the University of Bologna. Here, Cavalieri established a simple form of calculus, basing it on the scholastic conception of the indivisible, the point generating the line generating the plane by motion. Cavalieri, therefore, had no infinitesimals or atoms. He came to his results by the principle of Cavalieri, which concludes that two solids of equal heights have the same volume if plane cross-sections at equal heights have the same area. This allowed him to perform the equivalent of integrating polynomials. The gradual evolution of calculus was considerably stimulated by the publication of Descartes' Geometry, 1637, which brought the whole field of classical geometry within the scope of the algebraists. The book was originally published as an appendix to the Discours de la Méthode, the Discourse on Reason, in which the author explained his rationalistic approach to the study of nature. René Descartes was a Frenchman from Touraine, lived the life of a gentleman, served for a while in the army of Maurice of Orange, stayed for many years in the Netherlands, and died in Stockholm, where he had been invited by the Queen of Sweden. In common with many other great thinkers of the 17th century, Descartes searched for a general method of thinking to facilitate inventions and find the truth in the sciences. Since the only known natural science with some degree of systematic coherence was mechanics, and the key to understanding mechanics was mathematics, mathematics became the most important means of understanding the universe. Moreover, mathematics, with its convincing statements, was itself the brilliant example that truth could be found in science. The mechanistic philosophy of this period thus came to a conclusion similar to that of the Platonists, but for a different reason. Platonists, believing in authority, and Cartesians, believing in reason, both found in mathematics the queen of the sciences. Descartes published his geometry as an application of his general method of unification. In this case, the unification of algebra and geometry. The merits of the book, according to the commonly accepted point of view, work, consist mainly in the creation of so-called analytical geometry. It is true that this branch of mathematics eventually evolved under the influence of Descartes' book. But the geometry itself can hardly be considered a first textbook on this subject. There are no Cartesian axes, and no equations of the straight line and conic sections are derived, though a particular equation of the second degree is interpreted as denoting a conic section. Moreover, a large part of the book consists of a theory of algebraic equations, containing the rule of Descartes to determine the number of positive and negative roots. We must remember that Apollonius already had a characterization of conic sections by means of what we now call coordinates, and Pappus had in his collection a treasury of analysis, in which we have only to modernize the notation to obtain a consistent application of algebra to geometry. Even graphical representations occurred before Descartes, or Racine. Descartes' merits lie above all in his consistent application of the well-developed algebra of the early 17th century to the geometrical analysis of the ancients, and by this, in an enormous widening of its applicability. A second merit is Descartes' final rejection of the homogeneity restrictions of his predecessors, which even vitiated Wiete's logistica speciosa, so that terms like x squared, x cubed, and x times y were now considered as line segments. An algebraic equation became a relation between numbers, a new advance in mathematical abstraction necessary for the general treatment of algebraic curves. Much in Descartes' notation is already modern. We find in his book expressions such as a plus b times the square root of a squared plus b squared, which differ from our notation only in Descartes still writing a for a squared, which is even found in Gauss, though he has a cubed for a to the fourth power for a, etc. It is not hard to find one's way in his book, but we must not look for our modern analytical geometry. A little closer to such analytical geometry came Pierre Fermat, a lawyer in Toulouse, who wrote a short paper on geometry probably before the publication of Descartes' book, but which was only published in 1679. In this usage we find the equations y equals mxy equals k squared, x squared plus y squared equals a squared xa plus I equals b cubed, assigned to lines and conics with respect to a system of usually perpendicular axes. However, since it was written in Wiete's notation, the paper looks more archaic than Descartes' geometry. At the time when Fermat's usage was printed, there were already other publications in which algebra was applied to Apollonius' results, notably the Tractatus de Sectionibus Conicis, 1655, by John Wallis, and a part of the Elementa Curvarum Linearum, 1659, written by Johann de Witt, Grand Pensionary of Holland. Both these works were written under the direct influence of Descartes, but progress was very slow. Even L'Hospital's Trait analytique des sections coniques, 1707, has not much more than a transcription of Apollonius into algebraic language. All authors hesitated to accept negative values for the coordinates. The first to work boldly with algebraic equations was Newton in his study of cubic curves, 1703. The first analytic geometry of conic sections, fully emancipated from Apollonius, appeared only with Euler's Introductio, 1748. The appearance of Cavalieri's book stimulated many mathematicians in different countries to study problems involving infinitesimals. The fundamental problems began to be approached in a more abstract form and in this way gained in generality. The tangent problem, consisting of the search for methods to find the tangent to a given curve at a given point, took a more and more prominent place beside the ancient problems involving volumes and centers of gravity. In this search, there were two marked trends, a geometrical and an algebraic one. The followers of Cavalieri, notably Torricelli and Isaac Barrow, Newton's teacher, followed the Greek method of geometrical reasoning without caring too much about its rigor. Christian Huygens also showed a definite partiality for Greek geometry. There were others, notably Fermat, Descartes, and John Wallis, who showed the opposite trend and brought the new algebra to bear upon the subject. Practically all authors in this period, from 1630 to 1660, confined themselves to questions dealing with algebraic curves, especially those with equations of the form a times y to the m power equals b times t n power. They found, each in his own way, formulas equivalent to the integral of x to the n power dx equals x to the n plus 1 power divided by n plus 1, first for positive integer, n. later for negative integer and fractional n. Occasionally, a non-algebraic curve appeared, such as the cycloid roulette, investigated by Descartes and Blaise Pascal. Pascal's Trait General de la Roulette, 1658. Part of a booklet published under the name of A. d'Etonville, greatly influenced the young Leibniz. In this period, several characteristic features of calculus began to appear. Fermat discovered in 1638 a method to find maxima and minima by slightly changing the variable in a simple algebraic equation, and then letting the change disappear. It was generalized in 1658 to more general algebraic curves by Johannes Hud, a burgomaster of Amsterdam. There were determinations of tangents, volumes, and centroids, but the relationship between integration and differentiation as inverse problems was not really grasped, except perhaps by Barrow. Pascal occasionally used expansions in terms of small quantities in which he dropped the terms of lower dimensions. Anticipating Newton's debatable assumption that the product of two infinitesimally small quantities is negligible, Pascal defended his procedure by appealing to intuition rather than logic. Anticipating Bishop Berkeley's criticism of Newton. Scholastic thought entered into this search for new methods not only through Cavalieri, but also through the work of the Belgian Jesuit Grégoire de Saint-Vincent and his pupils and associates, Paul Gulden and André Taquet. These men were inspired by both the spirit of their age and medieval scholastic writings on the nature of the continuum and the latitude of forms. In their writings, the term exhaustion for Archimedes' method appears for the first time. Taquet's book, On Cylinders and Rings, 1651, influenced Pascal. This fervid activity of mathematicians, in a period when no scientific periodicals existed, led to discussion circles and constant correspondence. Some figures gained merit by serving as centers of scientific interchange. The best known of these men is the Minorite father Marin Mersenne, whose name as a mathematician is preserved in Mersenne's numbers. He corresponded with Descartes, Fermat, Desargues, Pascal, and many other scientists. Academics crystallized out of the discussion groups of learned men. They arose as opposition to the universities which had developed in the scholastic period, with some exceptions such as Leiden University, and still fostered the medieval attitude of presenting knowledge in fixed forms. The new academies, on the contrary, expressed the new spirit of investigation. They typified this age drunk with the fullness of new knowledge, busy with the uprooting of superannuated superstitions, breaking loose from traditions of the past, embracing most extravagant hopes for the future. Here, the individual scientist learned to be contented and proud to have added an infinitesimal part to the sum of knowledge. Here, in short, the modern scientist was evolved. The first academy was founded in Naples in 1560. It was followed by the Accademia dei Lincei in Rome in 1603. The Royal Society dates from 1662, and the French Academy from 1666. Wallace was a charter member of the Royal Society. Huygens of the French Academy. One of the most important books written in this period of anticipation is Wallace's Arithmetica Infinitorum, 1655. The author was the Savilian professor of geometry at Oxford from 1643 until his death in 1703. The title of his book shows that Wallace intended to go beyond Cavalieri's Geometria Indivisibilium. It was the new Arithmetica, algebra, that Wallace wanted to apply, not ancient geometry. In this process, Wallace extended algebra into a veritable analysis, the first mathematician to do so. His methods of dealing with infinite processes were often crude, but he obtained new results. He introduced infinite series and infinite products and used imaginaries, negative, and fractional exponents with great boldness. He wrote symbols for infinity, and claimed that -1 to the power of a half equals the square root of -1. Typical of his results is the expansion of pi as a product of fractions involving the squares of odd and even numbers. Wallace was only one of a whole series of brilliant men of this period, who enriched mathematics with discovery after discovery. The driving force behind this flowering of creative science, unequaled since the great days of Greece, was only partly the ease with which the new techniques could be handled. Many great thinkers were in search of a general method, sometimes conceived as a method of mathematics, sometimes more general, as a method of understanding nature and creating new inventions. This is why in this period all outstanding philosophers were mathematicians, and all outstanding mathematicians were philosophers. The search for new inventions sometimes led directly to mathematical discoveries. A famous example is the Horologium Oscillatorium, 1673, of Christian Huygens, where the search for better timepieces led not only to pendulum clocks, but also to the study of evolutes and involutes of a plane curve. Huygens was a Hollander of independent means who stayed for many years in Paris. He was eminent as a physicist and astronomer, established the wave theory of light, and explained that Saturn had a ring. His book on pendulum clocks influenced Newton's theory of gravitation, and along with Wallace's Arithmetica, represents the most advanced form of calculus in the period before Newton and Leibniz. The letters and books of Wallace and Huygens abound in new discoveries, in rectifications, envelopes, and quadratures. Huygens studied the tractrix, the logarithmic curve, the catenary, and established the cycloid as a tautochronous curve. Despite this wealth of results, many of which were found after Leibniz had published his calculus, Huygens belongs definitely to the period of anticipation. He confessed to Leibniz that he never could familiarize himself with Leibniz's method. Wallace, similarly, never felt at home with Newton's notation. Huygens was one of the few great 17th century mathematicians who took rigor seriously. His methods were always strictly Archimedean. The activity of mathematicians in this period extended into many fields, both new and old. They enriched classical topics with original results, cast new light upon ancient fields, and even created entirely new subjects of mathematical research. An example of the first case was Fermat's study of Diophantos. An example of the second case was Desargues' new interpretation of geometry. The mathematical theory of probability was an entirely new creation. Diophantos became available to a Latin-reading public in 1621. In Fermat's copy of this translation are found his famous marginal notes, published by his son in 1670. Among them, we find Fermat's great theorem that x to the n power plus y to the n power equals z to the n power is impossible for positive integer values of x, y, z, and n greater than 2, which led Kummer in 1847 to his theory of ideal numbers. A proof valid for all n has not yet been given, though the theorem is certainly correct for a large number of values. Fermat wrote in the margin beside Diophantos the first I8, to divide a square number into two other square numbers, the following words, to divide a cube into two other cubes. A fourth power, or in general any power whatever into two powers of the same denomination above the second, is impossible. And I have assuredly found an admirable proof of this, but the margin is too narrow to contain it. If Fermat had such an admirable proof, then 3 centuries of intense research have failed to produce it again. It is safer to assume that even the great Fermat sometimes erred. Another marginal note of Fermat states that a prime number of the form plus 1 can be expressed once, and only once, as the sum of two squares, which theorem was later demonstrated by Euler. Another theorem of Fermat, stating that a2 to the p minus 1 power minus 1 is divisible by p when p is prime and a is prime to p, appears in a letter from 1640. This theorem can be demonstrated by elementary means. Fermat was also the first to assert that the equation x cubed minus a times y squared equals 1, a non-square integer, has an unlimited number of integer solutions. Fermat and Pascal were the founders of the mathematical theory of probabilities. The gradual emergence of interest in probability problems is primarily due to the development of insurance. But the specific questions that stimulated great mathematicians to think about this matter came from noblemen gambling in dice or cards. In Poisson's words, a problem concerning games of chance, proposed by a man of the world to an austere Jansenist, was the origin of the calculus of probabilities. This man of the world was the Chevalier de Mere, who approached Pascal with a question concerning the so-called problem of points. Pascal began a correspondence with Fermat on this problem and on related questions, and both men established some of the foundations of the theory of probability, 1654. When Huygens came to Paris, he heard of this correspondence and tried to find his own answers. The result was the De Ratiociniis in Ludo Allier, 1657, the first treatise on probability. The next steps were taken by De Witt and Halley, who constructed tables of annuities, 1671. 1693. Blaise Pascal was the son of Etienne Pascal, a correspondent of Mersenne. The limicon of Pascal is named after Etienne. Blaise developed rapidly under his father's tutelage, and at the age of 16 discovered Pascal's theorem concerning a hexagon inscribed in a conic. It was published in 1641 on a single sheet of paper and showed the influence of Desargues. A few years later, Pascal invented a computing machine. At the age of 25, he decided to live the ascetic life of a Jansenist in the convent of Port Royal, but continued to devote time to science and literature. His treatise on the arithmetical triangle formed by the binomial coefficients and useful in probability appeared posthumously in 1664. We have already mentioned his work on integration and his speculations on the infinitesimal, which influenced Leibniz's Dara. Gerard Desargues was an architect from Lyons and the author of a book on perspective, 1636. His pamphlet with the curious title of Brouillant projet d'une attente aux événements des rencontres d'un cône avec un plan 1639 contains in a curious botanical language some of the fundamental conceptions of synthetic geometry, such as the points at infinity, involutions, and polarities. His Desargues' theorem on perspective triangles was published in 1648. These ideas did not show their full fertility until the 19th century. A general method of differentiation and integration, derived in the full understanding that one process is the inverse of the other, could only be discovered by men who mastered the geometrical method of the Greeks and Cavalieri, as well as the algebraic method of Descartes and Wallis. Such men could have appeared only after 1660. And they actually did appear in Newton and Leibniz. Much has been written about the priority of the discovery, but it is now established that both men found their methods independently of each other. Newton had the calculus first, Newton 1665-66. Leibniz in 1673-76, but Leibniz published it first, Leibniz 1684-86. Newton 1704-1736. Leibniz's school was far more brilliant than Newton's school. Isaac Newton was the son of a country squire in Lincolnshire, England. He studied at Cambridge under Isaac Barrow, who in 1669 yielded the Lucasian professorship to his pupil. A remarkable academic event, since Barrow frankly acknowledged Newton to be his superior. Newton stayed at Cambridge until 1696, when he accepted the position of warden, and later of master, of the Mint. His tremendous authority is primarily based on his Philosophia Naturalis Principia Mathematica, 1687, an enormous tome establishing mechanics on an axiomatic foundation and containing the law of gravitation, the law which brings the apple to the earth and keeps the moon moving around the earth. He showed by rigorous mathematical deduction how the empirically established laws of Kepler on planetary motion were the result of the gravitational law of inverse squares, and gave a dynamical explanation of many aspects of the motions of heavenly bodies and of the tides. He solved the two-body problem for spheres and laid the beginnings of a theory of the moon's motion. By solving the problem of the attraction of spheres, he also laid the foundation of potential theory. His axiomatic treatment postulated absolute space and absolute time. The geometrical form of the demonstrations hardly shows that the author was in full possession of the calculus, which he called the theory of fluxions. Newton discovered his general method during the years 1665-66, when he stayed at his birthplace in the country to escape the plague that infested Cambridge. From this period also date his fundamental ideas on universal gravitation, as well as the law of the composition of light. There are no other examples of achievement in the history of science to compare with that of Newton during those 2 golden years, remarks Professor Moore. Newton's discovery of fluxions was intimately connected with his study of infinite series in Wallis's Arithmetica. It brought him to extend the binomial theorem to fractional and negative exponents, and thus to the discovery of the binomial series. This again helped him greatly in establishing his theory of fluxions to all functions, whether algebraic or transcendental. A fluxion, expressed by a dot placed over a letter, was a finite value, a velocity. The letters without the dot represented fluents. Here's an example of how Newton explained his method of fluxions. 1736. The variables of fluents are denoted by v, x, y, z, and the velocities by which every fluent is increased by its generating motion, which I may call fluxions or simply velocities. Or celerities, I shall represent by the same letters pointed, thus y, x, y, z. Newton's infinitesimals are called moments of fluxions, which are represented by O Budau. xo, yo, zo. O being an infinitely small quantity. Newton then proceeds, thus let any equation x cubed minus a times x squared plus a times x times y minus y cubed equals 0 be given, and substitute x plus xo for x, y plus yo for y, and there will arise x cubed plus 3x squared, xo plus 3xo squared, plus o cubed, minus ax squared minus 2xo minus x, o squared plus axo plus axo minus y cubed, minus we co minus y cubed minus we cubed minus 3 minus yo cubed equals 0 tori. Now, by supposition, gebt minus ax squared plus axy minus y cubed equals 0, which therefore, being expunged and the remaining terms being divided by o, there will remain 3x squared, x minus 2x plus ax plus ix plus axy minus 3 plus cax exo minus 3 plus xeo minus 3oyo plus axio minus 3oyo plus equals. But whereas 0 is supposed to be infinitely little, that it may represent the moments of quantities, the terms that are multiplied by it will be nothing in respect to the rest. I therefore reject them, and there remains 3x squared x minus 2x plus a yx plus a x plus a y minus 3 squared y equals 0. 1 null. This example shows that Newton thought of his derivatives primarily as velocities, but it also shows a certain vagueness in his expression. Are the symbols O zeros, infinitesimals, or finite numbers? Newton tried to clarify his position with the theory of prime and ultimate ratios, introduced in the Principia, involving the concept of limits but in a way that was hard to understand. Those ultimate ratios with which quantities vanish are not truly the ratios of ultimate quantities, but limits toward which the ratios of quantities, decreasing without limit, do always converge, and to which they approach nearer than by any given difference, but never go beyond, nor in effect attain to, until the quantities have diminished infinitely. Principia I sect. I. Last scholium. Quantities. And the ratio of quantities, which in any finite time converge continually to equality, and before the end of that time approach nearer the one to the other than by any given difference, become ultimately equal, I, lemma, aware. This was far from clear, and the difficulties in understanding Newton's theory of fluxions led to confusion and severe criticism by Bishop Berkeley in 1734. The misunderstandings were not resolved until the modern concept of limits was well established. Newton also wrote on conics and plane cubic curves. In the Enumeratio Linearum Tertii Ordines, 1704, he classified plane cubic curves into 72 species, basing this on his theorem that every cubic can be obtained from a divergent parabola y cubed equals x cubed plus bx squared plus cx plus d by central projection from one plane upon another. This was the first important new result reached by the application of algebra to geometry. All previous work simply translating Apollonios into algebraic language. Another contribution of Newton was his method of finding approximations to the roots of numerical equations, which he explained with the example x to the power of n minus 2x minus 5 equals 0 do height, which yields x equals approximately 2.9455147. The difficulty in estimating Newton's influence on his contemporaries lies in the fact that he always hesitated to publish his discoveries. He first tested the law of universal gravitation in 1665-66, but did not announce it until he presented the manuscript of most of the Principia to the printer in 1686. His Arithmetica Universalis, consisting of lectures on algebra delivered between 1673 to 1683, was published in 1707. His work on series, dating from 1669, was announced in a letter to Oldenburg in 1676 and appeared in print in 1711. His Quadrature of Curves from 1671 was not published until 1704. This was the first time that the theory of fluxions was presented to the world. His method of fluxions only appeared posthumously in 1736. Gottfried Wilhelm Leibniz was born in Leipzig and spent most of his life near the court of Hanover in the service of the dukes, one of whom became King of England as George I. He had an even wider range of interests than other great thinkers of his century, encompassing history, theology, linguistics, biology, geology, mathematics, diplomacy, and invention. He was one of the first after Pascal to invent a computing machine, imagined steam engines, studied Sanskrit, and promoted the unity of Germany. The search for a universal method to obtain knowledge, make inventions, and understand the essential unity of the universe was the driving force of his life. The Scientia Generalis he tried to build had many aspects, leading to discoveries in mathematics. His search for a Characteristica Generalis led to permutations, combinations, and symbolic logic. His search for a lingua universalis to eliminate errors of thought led to symbolic logic and many innovations in mathematical notation. Leibniz was one of the greatest inventors of mathematical symbols, understanding the unity of form and content. His invention of calculus resulted from his search for a lingua universalis of change and motion in particular. Leibniz discovered his new calculus between 1673 and 1676, under the influence of Huygens, and by studying Descartes and Pascal. He was stimulated by the knowledge that Newton was reported to have such a method, while Newton's approach was primarily kinematic. Leibniz's was geometrical, thinking in terms of the characteristic triangle, dx, ds, which had already appeared in several other writings, notably in Pascal and in Barrow's Geometrical Lectures of 1670. The first publication of Leibniz's calculus appeared in 1684 in a 6-page article in the Acta Eruditorum, a mathematical periodical he founded in 1682. The paper, titled Nova Methodus Pro Maximis et Minimis Turoctoi, idem quoque tangentibus, quae nec fractus, nec irrationales quantitates moratur, et singulare pro illi calculi genus, was a barren and obscure account, but contained symbols dx di and the rules of differentiation, including the product rule and the quotient rule, with the condition di equals 0 for extreme values and d squared y equals 0 for extreme values. For points of inflection. This was followed in 1686 by another paper with the rules of the integral calculus, containing the integral symbol. An extremely fertile period of mathematical productivity began with these publications. Leibniz was joined after 1687 by the Bernoulli brothers, who eagerly absorbed his methods. Before 1700, these men had discovered most of our undergraduate calculus and important sections of more advanced fields, including solutions to some problems in the calculus of variations. By 1696, the first calculus textbook appeared, written by the Marquis de l'Hospital, a pupil of Johann Bernoulli, who published his teacher's lectures on differential calculus in the Analyse des Infiniment Petits. This book contains the so-called rule of l'Hospital for finding the limiting value of a fraction whose terms both tend toward 0. Our calculus notation is due to Leibniz, including the names calculus differentialis and calculus integralis. Because of his influence, the equals sign is used for equality and the dot for multiplication. The terms function and coordinates are due to Leibniz, as well as the term osculating. The series for pi, involving alternating odd fractions, are named after Leibniz, though he was not the first to discover them. This credit goes to James Gregory, a Scottish mathematician who also tried to prove that the quadrature of the circle with compass and ruler is impossible. Leibniz's explanation of the foundations of calculus suffered from the same vagueness as Newton's. Sometimes his dxi Die were finite quantities. Sometimes quantities less than any assignable quantity, and yet not zero. In the absence of rigorous definitions, he presented analogies, pointing to the relation of the radius of the Earth to the distance of the fixed stars. He varied his approach to questions concerning the infinite. In one of his letters to Fouché, 1693, he accepted the existence of the actually infinite to overcome Zeno's difficulties, and praised Grégoire de Saint Vincent, who computed where Achilles meets the tortoise. As Newton's vagueness provoked Berkeley's criticism, Leibniz's provoked Bernard Neuentie's opposition in 1694. Both criticisms were justified but entirely negative, unable to provide a rigorous foundation for calculus, inspiring further constructive work.